lecture. So let's go back once again to where we were yesterday. So just a quick recall. In the first class, I talked about the beginning of this field of optical lattices. And yesterday, I presented some of the things that were done after the quantum gas microscope was developed. And today is kind of a futurology exercise when we can think maybe together what can be done next. So, before I start, there is quite a difference between a wild guess and an educated guess. So the educated guess comes from a very peculiar point of view. Once again, if you had here somebody who is from optics or atomic physics, probably he would give or she would give a completely different perspective of what's next to come. But from my point of view, I have some ideas that I would like to share with you. So there are different subjects that I think will advance in the near future of this area. And one of them is high-TC superconductivity. So we discussed it yesterday. Oh, there's the better. So I've shown this phase diagram. Oh, maybe it's out of battery. But I've shown this phase diagram of the high-TC superconductor more than once in this school. And so what we have achieved so far in the experiments that I'm shown yesterday is that region over there with no or small doping, and within this orange area, which is the antiferromagnetic Mott insulator. So this area was achieved in experiments, and to me, it's very clear what's next in this field is going to lower temperatures and trying to observe what happens in the dome of the high temperature superconducting phase. So experiments in the actual cuprates show that this phase has what we call a D-wave symmetry. So the Cooper pairs that are formed, the pairing electrons, they don't have the S-wave symmetry of the BCS theory. They have some different pairing. And one thing that is very, very interesting is when we study the Hubbard model, not the high TCs, what's the symmetry of the pairs that are formed? So I think this is a first step to find the pairs and check the symmetry, whether the symmetry matches the high TCs or is something different, and observing the superconductivity. And as I've shown yesterday, the more recent experiments that have reached very, very low temperatures might be able to reach this region of the phase diagram. And I say might because this is a region of the phase diagram that theory doesn't have access. So different from what we have seen in the Costa-Litals transitions, when we have very clear bounds for the critical temperature, we don't actually know what the critical temperature is here. So this is something also very interesting to be on the look at of, you know, the open things that can be done in high TCs. And I'm really willing to bet that people like Marcus Greiner, that has put up this paper with this very, very low cryogenic temperature, is now working towards that. Because I think the person that observes the temperature, the superconductivity, and understands how it works on cuprate-like systems on the high TCs is very much on the front run for a Nobel Prize. This is a problem that the cuprates were first synthesized in '86, so it's a lot of years since, you know, they first were seen. And we still don't know how they become superconductors. Of course, we've learned a lot over the course of the years, but this is like the holy grail for the community. So I think this is like one major thing that experimentalists are going to go for. The other thing that I think will be on the look out over the next years is geometry. So I've shown you these plots before. The one in the left is in Emmanuel Bloch's groups. It's quite old, actually. It's 2012. This is more recent, the triangular lattice in 2021. And the idea is not, oh, I've done this in the square lattice, then I'll do on the triangular, on the honeycomb, and just repeat and repeat just because you want to repeat. The idea here is, what is the new physics that emerge when I have a different geometry? And I'll say some of the new physics that are coming out already and will come out on the next years. The first one is frustration. Michel Brun had a very similar sketch as this one. So when we have a triangular lattice with antiferromagnetic interactions, what happens is you have one spin, and the next one will be pointing in the opposite direction. And then the third one, it doesn't know whether it wants to be antiferromagnetic to the black one or to the red one. And this is why what we call frustration. So there is no way to satisfy all the relations at the same time. And this leads, as you can imagine, to a very degenerate high ground state, because you can have, you know, in a large lattice, many different options and large entropy and a very different physics than in the square lattice. The first experiments are already going on, and so this is a nice way to study frustration. There is the square lattice, and you put up a hopping in the middle T prime, and if T prime is 0, then it's square lattice non-frustrated, and if T prime is 1, you go to the full triangular lattice, and this is a way of studying frustration in a very controlled way. And this is this 2021 article that shows what happens to the spins correlations. They change sign as we increase T prime, and you can see the behavior in the square lattice, which is already very much studied, going towards the triangular lattice, and you see how frustration is put in step by step and what's going on in there. So this is one of the many things that can be done and will proceed to be done in the following years. Another geometry that I think is very, very interesting is the Kagome lattice. There are no current experiments for the Kagome lattice with fermions. This one is for bosons in Dunstan-per currents group. And why is the Kagome lattice so interesting? It's also frustrated, as in the triangular lattice. You can see here on the left side, there are triangles that are connected to hexagons, and the triangles are frustrated, so there is the effect of frustration. But on top of that, if we look at the band structure of the Kagome lattice, it has 2 bands, and on top of these 2 bands, a flat band. So a flat band is a band with no dispersion. It's flat. That's why it's called a flat band. And what happens is also it's very degenerate. The fermions that sit on this band, they all have the same energy because all the band has the same energy. And so it leads to very peculiar properties. And another interesting thing about the Kagome lattice is it is able to provide adiabatic cooling. I have not discussed much about this, but this is a plot of the entropy as a function of temperature for the Kagome lattice and different values of the interaction strength U. And you see they more or less cross around log 2, around there. And if you're on a higher temperature than that, on a higher entropy, as you increase U, you go from left to right. And so if you increase U keeping a constant entropy, a horizontal line, you increase the temperature of your system. On the other hand, if you start below the crossing point, what happens is you increase U and you decrease the temperature of the system. So this is a very nice way of cooling your atoms on a Kagome lattice. If you manage to reach the starting point um, below the log 2 entropy, then just by increasing the interaction strength, you cool your system. And this has been known for some shape geometries of lattices, and here is a comparison with what happens in the Kagome, honeycomb, and square lattice. And we can see if we start here as with a temperature around 0.4 in hopping units and keep increasing you reach 0.3. And so this is an interesting property of the Kagome lattice that might be useful when realizing these for fermions. Another lattice that is very interesting is what we call the Lieb lattice. So this is the square lattice where we remove one atom in the center of each square. You can be seen in there. And this is interesting because this is the lattice in which the cuprates have their 2D planes. So the cuprates have this lattice where in the vertex you have a copper, and in the 2 atoms that are there, the 4 atoms surrounding it that are in red there, you have the oxygen. So this is the actual lattice of the cuprates that lead to high TC. So a lot of people study this lattice because of that. Here is a proposal by LICAM to realize this within optical lattices. And once again, like the Kagome lattice, it has a flat band. And the flat band here is not on the top, it's really in the middle. So if we're looking at properties at filling, the flat band is going to play a more important role here than in the Kagome lattice. So it took me a while to visualize that, but the same way we can go from the square to the triangular lattice by adding a hopping, here we can go from the Lieb to the Kagome by adding a hopping. So when we draw the Kagome like we draw here in the middle, the dotted line linking the green and blue triangles, when it's erased, we are on the Lieb limit. So the Lieb lattice is not frustrated, and the Kagome lattice is frustrated. So it's a way of analyzing the effect of frustration in another instance. But more than that, we know that the Lieb lattice has a ferrimagnetic ground state, and in the Kagome lattice, it's not so clear what happens to the magnetism. And we did a study 2 years ago by, similarly to what was done with the square to the triangular, from the Lieb to the Kagome lattice. And what we see, different phases here. We have a region where we have a paramagnetic metal, and if we increase U, we reach the Mott insulator. But if the hopping is too small and we are more on the Lieb lattice size, then we have a ferrimagnetic insulator. So different phases that are driven by geometry, and with optical lattices, you can possibly go from one to the other. And another type of geometry that is very, very interesting, and we have some interesting results that I'll talk about in a minute in cold atoms, is the ladder. So the ladder is when you have 2 chains that are linked to each other, and the linkage is like the rung of the leg, and then you have the legs. And this has very interesting physics related to topology that I'll talk more in a bit. But when we think of what can be done with varying geometry and what we'll be seeing in the next years, so my bets go to observing magnetic properties of frustrated systems, that because this is already starting. Ferrimagnetism that can be tuned in when you arrange the geometry. Quantum spin liquids. Michel Brun have just mentioned a work that saw spin liquids with optical tweezers. This is a very interesting phase of matter. It's hard for theories to understand because there is no clear mark of the spin liquid. So many proposals and many different kinds of spin liquids, chiral spin liquids. And so I think there will be some attention devoted to that. The interplay between frustration and Mott physics can lead to novel phases. Flat bands are attracting very recently a lot of attention. And with the flat bands, topological properties that I will mention now. So I'll talk briefly about topology and topological properties. And this is a very hot subject that has led to the Nobel Prize in 2016 to 3 people. And so topology and topological phases. And I'll speak a little bit about by both. Actually, about topological phases, Kosterlitz and Thouless that won the Nobel and named the Kosterlitz-Thouless phase transitions are one type of topological phase, and we have discussed this yesterday, and that this can occur in the attractive Hubbard model with doping or repulsive Hubbard model with a spin imbalance. And the experiments that were done, I don't have the dates here, but in 2016, 18, and 19, had a very high temperature of 0.45, marked in the gray area in the plots. The Kosterlitz-Thouless temperature is 0.15, but this year's experiment is below that. So to me, what next is very clearly going there and checking, observing these phases now that the temperatures are available. So I think this is a very clear next step. Regarding topology, it's a whole new field. It's new to me, so I don't know very much about this field. And I asked Marcelo Neto, who is down the hall in my institution, who has been working with this for longer, to help me out. And so what the idea is, how we connect things that have very different topology as donuts and knots. And it's clearly that one cannot be transformed in the other. But when we have like a donut and a mug, you know, they both have a hole in the middle, and so you can manipulate one to lead into the other, but that's not going to be the same with the sphere. And the idea is that Hamiltonians can be described by some parameter that I'm calling C, that shows how, if one can be deformed into the other. Here, C is the number of holes. 1 hole is 1, 2 holes is 2. And this area in condensed matter has attracted a lot of attention, and also in optical lattices. So before I start, I found this review, and I think it's really a neat review on topological bands in this context of ultra-cold atoms. So I just thought I'd flag it out to you, so maybe you want to see. And I've mentioned already 2 Nobel Prize winners on topological states that are Kosterlitz and Thouless, but now I'm going to speak about Haldane. He proposed this model in 1988, and this model is a simple model. You have hopping from the sites that are black and white in the center, a regular hopping. You have second-year neighbor hopping, so between whites or between blacks, with a phase phi, a complex phase phi. And you have some M, which is a non-site energy that is different in either one of the sites. And the phase diagram is just like this one here, where nu equals 0 is the trivial phase, and nu equals plus or minus 1 is a topological phase. And when you read his paper, he says that I marked while the particular model presented here is unlikely to be directly physical realizable. And he goes on saying it's interesting anyway, but he had no hope it would be realizable. And in 2015, this same model was realized by the group of Tillman-Esslinger with optical lattices. This is a super, super cool experiment where they see exactly the diagram that Haldane has proposed. So I'm not sure this is the first topological study with cold atoms, but I think it's the coolest. So I've chosen to show this one. So as I mentioned before, I am interested in strongly correlated systems where we have interactions. And how can we say a system is strongly interacting in a topological state? So usually we look for a topological invariant that could be that C, which is the Chern number, or nu, some number that tells me whether the system is in a topological phase or not. And the usual prescription goes like that. You write your Hamiltonian in K-space, you get the wave function in K-space, you find the Berry curvature, you integrate over the Brillouin zone, and this gives you C, and C is your Chern number. If it is 0, then your system is trivial. If it is non-zero, then your system is in a topological state. And this seems to work very well. This is measurable in optical lattices, so I haven't spent much time reading and understanding this paper, but it's something similar to doing an Aharonov-Bohm experiment where you have a flux and you make your electrons go around. Here you have, you know, a system that's topological, and you have something circulate about it and evaluate the Berry curvature. So when we think about the interplay between topology and correlations, we go back to that list that I had made before of the things that people in condensed matter like, but sometimes cannot use. And I mentioned band theory, Landau theory of phase transitions, and BCS theories that fail when correlations are present. And now I added the topological invariant to this list because it also fails when correlations are present. So we have to come up with something else to say whether a system is strong in a topological phase or not. There are things that are currently used, usually, most of the time, in topological states, you have edge states. Something happens in the border of the state. But the thing is, you have the edge states, but the presence of the edge states does not guarantee that your system is in a topological phase. Some types of hidden order are often present, but the presence of some hidden order does not guarantee. And so we have to try to cover all we have to probe whether we have a topological state or not. And so this experiment that I have shown for the sketch of the Hubbard ladder done by Emmanuel Bloch's group probes exactly that. So it's a ladder where he kind of pulls it to the side and has one extra spin living alone, an extra side living alone in here, in the bottom, and to the left, and another one in the right. And you have hopping along the rungs with a given value, hopping along the chain with a given value, and this system turned out to be topological. He measured edge states and the hidden order string correlator that I will talk about in a bit. So for us to understand why this system and the system I'm going to present in a while are in a topological phase, I will talk a little bit about Haldane conjectures for spin chains. So apart from proposing that model that was observed in realized in optical lattice experiments and is in a topological phase, Haldane gave contributions to what happens in spin chains. And spin chains are very different whether you have an integer spin or a half integer spin. You have bosons and you have fermions, and we've been talking about this for a while. So when you have a half integer spin, you have levels that as you approach the thermodynamic limit, your L, which is the size of the chain, goes to infinity. These levels get closer and closer and closer, and there is no gap. So nothing much happens. On the other hand, if you have an integer spin chain, you have a gap from the first level, not to the second level, and this became known as the Haldane gap. So if I blow up this picture a little bit, there is the ground state. Above it, there is the first level, which is not a single level, it's a triplet, which has become known as the Kennedy triplet, and has edge states. So the edge states are starting to show up here, and above it, there is this Haldane gap, which is larger and does not go to zero when your system is very large, and is the Haldane gap. And as I said, we have edge states here. So the first time this system was studied was not for the Hubbard ladder, it was actually for the Heisenberg ladder. I would jump it. It shows different, so I'm getting lost. So the Heisenberg model is the strong coupling limit for the Hubbard model. In it, when you have the correlations are too strong, the electrons or the fermions stop moving around and they freeze in different size, and you have only one fermion per site. And you have J being the exchange coupling between the fermions in different sites. And here, this group studied this chain which has exchange along the rungs in the perpendicular and in the diagonal, and even a magnetic field. But even in the absence of the magnetic field H, when H is 0, there is a narrow region where we have a Haldane phase. So we decided to study a Hubbard ladder. And this is the work by João Pedro. He is a PhD student with me now. And what he studied is a two-leg Hubbard model that looks like that. We have hopping T along the legs, only 2 legs. We can have ladders with more legs, but here only 2. Diagonal hopping TD and a perpendicular hopping T perp. And this TD leads to frustration. And the questions we wanted to answer are, is the Haldane phase there when we don't have U going to infinity in the Heisenberg limit? And charge fluctuations are allowed? And what happens when we move away to from symmetry points when, you know, or all the hoppings or all the exchanges are the same? And instead of telling you bit by bit how we find that, I'm telling you first the answer, and I'm telling you bits of how we found that. But this is the phase diagram we found. The y-axis is the correlations, U. The x-axis is the diagonal hopping, and we use T as our scale, so T is always 1. And what we see, we do have this dome where we have a Haldane phase. And how do we probe that? We look at it into edge states. We look at into evenly degenerate entanglement spectrum, hidden antiferromagnetic order. We looked at the Kennedy triplet to see if it's there, and the Haldane gap. I'm not showing all the data now, but I'm just to give you a flavor of what is the physics that is going on there. When we have no diagonal hopping, we expect this antiferromagnetic phase to show up. So in one rung, we have up and down, and in the other rung, we have the opposite. And we have an antiferromagnetic state. And when we look at that, we see that when we don't have diagonal hopping, the blue region is negative, so we are seeing up and down, and the pink region is the other way around. So when we increase the diagonal hopping, something is different, and you can look at the diagonal correlation, it also shows the same. And if we look at in the magnetic structure factor, it shows the same. So what's going on here is as we increase the diagonal hopping, we move from something that looks like that, antiferromagnet, to something that looks like that. It is antiferromagnet along the chain, but it's ferromagnet within each rung. And when we look at it, we see that each rung is now S=1 state. And so this relates to the Haldane chain. And we see all the things that Haldane have predicted. Border states, the Haldane gap, and I'm not showing everything to you, but I'll show first the edge states, because the first time João showed me that, I thought he had made a mistake. Because when he looked at in a region outside the dome, which is the first plot, which is in TD = 0.6, so outside the dome, you look at the correlations of the rung with the next neighbor rungs. You start in the edge of the ladder, and you go moving, and the correlations go to zero very, very fast. But if you're inside the dome, they go to 0, and then they come back from 0. And this is very peculiar, and it's a very clear signal that we have edge states, and he was able to calculate the correlation length of the edge state, which is plotted here as a function of the diagonal hopping, and it blows up in the border of the this dome-shaped region. We also probed hidden antiferromagnetic order, as we have in the rungs a spin 1 entity. It can be pointing up, pointing down, or 0. And this 0 messes up the antiferromagnetism. So if we look at the antiferromagnetic operator, it goes to 0 because you have the zeros, and it breaks the ordering. But the string operator, where this middle part here kind of removes the zeros that are in the middle, it has a very clear sign. And this is the outcome and the phase diagram I've shown in the beginning. So the idea here is that the interplay between geometry, symmetry, correlations, and topology can be studied in a setting like that. And once again, optical lattices are really perfect for that, because you have control and you can switch your interaction. So you can just increase U and cross this dome shape and see outside the dome and inside the dome, and possibly make changes in your settings so you can change the diagonal hopping. It's not that easy, but to cross along the TD direction. So in general, what is next in this field? I think this field is going to be very, very active in the years to come. The understanding of topological states have advanced a lot in recent years. Specifically, when we have no correlations present, there is the very clear prescription on how to calculate Chern number or Zec phases, and how to understand what happens when we have topology. But in the presence of correlations, this is much less clear, so there is a lot to be done in this field, and I think optical lattices is a very good setup for that. Different geometries, I've shown here a ladder, but there are many different geometries that can lead to topological phases. Flat bands are kind of a flag that a topological phase can happen. So possibly, you know, in Lieb lattice or Kagome phase, there could be something. And I've only talked about the Hubbard model, but there are many, many different models. So Haldane model and Haldane model in the presence of correlations. So Esslinger has shown that the Haldane phase is there when no correlations are present. He could tune in the correlations and see what happens. Some experiments are being done with that, and the SSH model, the Suchriffer-Heger, that Michel Brun mentioned this morning, also has topological phases and topological phases in the presence of correlation. So many different things are to be expected in this settings. So one of the things I think is interesting and we should be in the look at is dipolar atoms. So there is this very, very nice experiment by Francesca Sferlaino group in 2016, where she studied dipolar atoms. It's erbium atoms, but bosonic atoms in an optical lattice. And so the interesting things is all dipoles point in the same direction in this experiment. And the dipole-dipole interactions are long-ranged by nature. They fall with 1/3, and they are directional. So depending on where the local moment is pointing, it can be repulsive, it can be attractive, and it leads to many possibilities of interesting physics. So far, no dipolar atoms, fermionic atoms on optical lattices. So I think this is something that could be done in the next years, and is something very interesting. So it's not there, but we can calculate, maybe, you know, help experimentalists. So we took a shot at that by looking at this model where the interactions look like that. So it's dipolar-like, but we have truncated it looking into first neighbor interactions. We done exact diagonalization. This is hard to do with quantum Monte Carlo. And we found so many phases that we were just amazed, you know. So on top of each view graph is the angle theta. Let me go back here. So, So theta is the polar angle in which the dipolar atom is pointing. So there is the angle theta and the angle phi, and change theta, phi, and v, the intensity, we get all these very different phases. So for theta equals 0.22, we have a Mott insulator, XS, which is a separate phases along the X direction, Y direction, charge CDW, checkerboard CDW, and here the phases move and enhance and increase as we change theta, and here are sketches of, you know, the different phases, what they look like. So many, many different phases just by adding, you know, a dipolar with, and we didn't even consider long range, just adding V and V with a given polar angle and azimuthal angle. So there are other studies, these ones done through Quantum Monte Carlo of the extended Hubbard model, and extended here considering V uniform, just near neighbor and equal in all directions. But you can see the phase diagram is very rich. So for the Hubbard model, which is just what we get when we have V equals 0 in the square lattice, we have in the attractive case S-wave superfluidity, and in the repulsive case an antiferromagnet with a Mott insulator. And when we add this V axis, then we have charge density wave, D wave, phase separation, so different phases arise. And so I think looking into that, into optical lattice, should be really, really cool to do. And here is what happens in the honeycomb lattice. So in the honeycomb lattice, when it's attractive, we have S-wave. When it's repulsive, you have a semi-metal, and beyond some critical value of U, you have an antiferromagnet. And when you add this layer, you also see CDW, phase separation, and so new phases arise in both cases. So what to expect in this next years to come? I really expect, I really hope Francesca Fellaino will put fermionic atoms in an optical lattice, because there is a lot to be seen. And so the physics of the extended Hubbard model, I've shown into geometries, but you can think of more. Longer range interactions, not only next neighbor, but if you have really long range interactions. Anisotropic interactions, what happens when the interactions are not equal. We have a taste of it in what we've seen. The physics of phase separation is not very well studied, and it arises in when we have longer range interactions. So this is something that could be really interesting to look at. And charge density waves that are present in the cuprates, are present in many instances and arise in this case. So the possibility to study charge density waves within this context, I think, is a great thing. So the next thing I think is interesting to look in the following years is at the SUN physics. And here I want to relate to something that Carla said. I don't work with SUN physics. How did I find about the SUN physics? So I follow a given researcher on Google Scholar. Whenever he publishes a paper, I get an email, and I saw SUN physics, and I said, oh, that's different. Let me check it out. And so that's how I found about this paper. So follow some people you think do interesting things, and you will get to know. So when, sorry, when in the first class, I mentioned that the fermionic people work in two teams, the lithium team and the potassium team. And what is the two teams have in common is that they work with two species. And I call them spin up and spin down, but they are just different hyperfine states. And this defines the SU2 physics. We have two species here. So what this group is doing, and there's more than one published paper on that, is studying what happens when you have SUN, and N is larger than 2. So they look here at ytterbium atoms and in different independent nuclear spin states. So you can have 5 halves, 3 halves, 1 half, minus 1 half, 3 halves, and minus 5 halves. And they can separate, so they can use the 6, or only 2, or only 4, or only 3. And they do the modeling in the context of optical lattices and calculations of the the SUN Hubbard model. And so I think there is a lot of different physics coming out of that, and they started to look at correlation functions, and with one species, the other species, and how they fall with distance compared to the SU2 regular case, and in 1D, in 2D. So I think it's really an open door to new physics, to explore this physics, and I think the sketch there is really nice because it shows, you know, the SU3, the SU4 and the SU6, and what they are looking into that. So this is like a brand new field to explore the SUN Hubbard model. So in this context, what's to be expected? I think I don't even know what to expect because this is really new. But higher order symmetry is certainly going to arise because you have, you know, instead of the SU2 group symmetry, you're going to an SUN, and then N can be 6. New phases, new phase transitions. So I think this really is an open door to new and interesting physics. And so I'm kind of coming to the end of what I am talking about. And so just to remember, I've made some choices. And it's not like what I didn't talk about is not happening or is not important. One thing I did not talk about was this whole world of quantum spin chains that are realizable within optical tweezers, and Michel Brun talked about this morning. There is a lot of things going on there, and qubits, quantum information, scalability, and I am not going to dare to talk about something I don't work with, but you know, there is a lot happening, and it's in the intersection with, you know, things I am interested, because frustration, magnetism, it's really close contact. But just to mention a few of the things I have not talked about but are like booming. So non-equilibrium physics, I didn't even mention. There is a lot happening. Floquet engineering, dissipation, so a lot going on. Synthetic dimensions, there is a group in Florence working with that, and I think some interesting physics can come out of it, but I don't really follow it closely. Entanglement, there is a lot of proposals of entanglement and studying and using it for quantum information and quantum computing in this setting. I am not discussing that. Clocks and metrology, next week I'll be here for another school, and Ana Maria Rey is going to be here. She is the person that does a lot of things with clocks and metrology. So in the setting, there's a lot of physics in there. Disordered systems, this has been going on since the early days. There's very nice work from Alain Speck with bosons and also with fermions, so studying phase transitions and localization transitions and putting disorder by hand with speckle noise in a controlled way. There's a lot of things going on and very interesting physics. Artificial gauge fields, I don't follow this closely, so I wouldn't know what to talk about, but I know this is kind of booming now. And integrations, the integration between these systems and other systems like optical lattices and photonic systems is also starting to happen, and I think it's interesting to keep an eye on. So just to finish, I want to say that I really believe it's strategic to have optical lattices being done in Brazil. So I think Patricia is the one who, she's hiding, but I think it's really important to have this sort of experiments done here, because we learn a lot of physics. And just as a final comments, I hope I have, I tried to show to you that optical lattice is an excellent platform to study emergent phenomena that we are interested in condensed matter physics. I mentioned most, but in other areas as well. The interplay of correlations, that's what I'm always interested in, and geometry, topology, symmetry, and other stuff that can be, you know, tailored in these experiments lead to new and interesting physics. So I think this is why so many people study that. And although, you know, I've shown many things that have been done over the last 30 years, I think that we have open and interesting questions still. And as the developments in the experimental side happen, we start to think of what other questions we can ask. And so this is an ongoing process. So there is still a lot of work to be done. So if you want to join this field, I think it's still an active, very active field. And with that, I thank you for your attention.
So questions? Yes.
Everybody's hungry.
Yes, hungry and tired. So actually I had one. Thereza, could you go back to, wait, I wrote it down. I had one that I always thought that having edge states was a proof of a topological
Yeah, so
protected
I
state.
thought
so this
that
was really surprising for
I
me.
thought that myself, but when you talk about with the expert in the fields, they say it is a condition, but it's not. If you don't have edge states, you don't have topology. But if you have edge states, you don't necessarily have topology.
But how they sustain themselves, because what I understand from edge states is something
So you
that
can
is
have
going to
edge
be
currents, edge magnetism, it depends on the system. But for instance, would you say the Meissner effect is a topological state? So just because you have edge currents doesn't mean you are in a topological state. If you don't have, then you're not. But and this was surprising to me because, you know, I think I still have a lot to learn about topology. But the first thing I've learned is that when you don't have like a Chern number or a Zach phase to show, then it's a lot more trickier. And what the people in the field accept, and it's something I didn't even show, is the entanglement spectra. So the entanglement spectra has to have pairs of states with the same energy. So the entanglement spectra is in pairs when you are in the Haldane phase. And this is what people accept as a marker of a topological state, a definite marker. So if you have this, then it's a topological. But it took me a while to understand the field and find out what I have to calculate to show people that indeed this is a topological state.
Okay. Another question? No? Maybe I have one last. So about the dipolar gases, actually, you showed a phase diagram. And I wanted just to be sure, what is V? So before, after?
Yeah, so it's here. So V is that value of the next near neighbor interaction. And it's like V is directional. It changes with theta and with phi, but V is the value. And we measure things regarding U. So it's V over U.
Okay. So it's really the dipole interaction strength, the V you are plotting there.
Yeah. So, and I find it very interesting that they all point in the same direction. And this happens in the experiments, and they are all pointing.
And these phase diagram graphs are all for zero temperature?
Yeah.
Okay, zero temperature.
Yeah, so when you increase the temperature, you're going to melt these phases.
Okay. Any other? You're too sleepy today. So let's thank Thereza again, and we go lunch.